Hi everyone, this is an after recording of my talk giving at the HiPIMS Today 2024 conference. First, I would like to thank the organizer a lot for giving me this opportunity to talk about HiPIMS from a historical perspective. It's a bit biased towards cutting tools because I spent many years in this industry. When giving this kind of historical talks, I think it's very difficult to tell a fair and unbiased story, but I will do the best from my point of view. So let's start from the beginning. This is the first paper that I am aware of that it's something similar to HiPIMS, and it's often referred to as the original paper. And it's from Moskvin, Kodachenko, and Fetisov, and was made at the Moscow Engineering Physics Institute. They applied the high power pulses to a planar magnetron and got into what they call a high power quasi-stationary low pressure discharge. And they used voltages in the range of 450 to 1000 volts and mentioned about cathode current densities of up to 25 amperes per square centimeter, so very high. And the image shown here to the left, it shows the voltage and current characteristics they saw, and the top three curves here are for the planar magnetron. And in this work, they used a copper and titanium target. And at the end, they conclude that the properties of the discharges are expected to open up new fields of applications. And today, I think we can say that they were correct. The research done in the former Soviet Union and later Russia about these pulsed high current E cross B discharges was brought into attention into the Western world by Vladimir Kuznetsov. And Mr. Kuznetsov was also the initiative taker to start the company called Chemfilt AB in Sweden. The original idea was to use the high density plasma for waste and chemical treatment, and thereby the name. And Chemfilt, they built this high current pulsar, but soon realized that this could be used also for magnetron sputtering to produce films. At this time, contacts were made to Linköping University and Professor Ulf Helmersson, and trials were initiated. And here to the right is two images of the original power supplies, and just as a reference, this is the size of a small desk, and it's quite heavy and not very flexible. And the only thing that could be changed was the peak voltage. Chemfilt applied for the first patent with Mr. Kuznetsov as inventor. This one has a WO priority date of March of 1997, and it was granted in the US in October 2001. This patent has been a subject for a lot of discussions, and the reason for that is that it was claimed that the discharge goes through an arc discharge before entering a fully ionized state. I'm not sure if this is still fully cleared, but in any case, the patent has expired now. I think after many years, this was also granted in Europe, but I could not find the information around that. So maybe someone at Semicon can tell us this story. We'll come back to that. The inventor also claims that they get complete ionization and that the target erosion is more uniform compared to DC sputtering. The first paper from the West came in 1999, and it was written by Kuznetsov together with Machak, Schneider, Helmersson, and Petrov. And in this work, they operated HiPIMS on a copper target, and they operated up to 2.8 kilowatt per square centimeter, so this is very high peak power. They observed a peak ion current density of 3.4 ampere per square centimeter, which is a very high number. And they also estimate the ionized flux fraction to be around 70% by deposition rate measurement. And they also conclude a better target erosion profile and better film coverage on the substrate compared to DC sputtering. And this paper has been cited more than 2,000 times according to Google Scholar. These pictures are probably taken around the early 2000s. Around this time, me and Professor Easarian from Sheffield Hallam University were working together on some HiPIMS tests. And back in the days, Sheffield Hallam University and Linköping University collaborated on some of the papers. At this time, we were always afraid of the high power and the high voltage, and we used to turn on all the things with using a long broomstick. We created many sparks and bangs, but we survived. To the left here is the picture of the old vacuum system we used. It's called Coin. This is where we made most of the early experiments. And this is had a chamber lid that was operated by pressure air, and this was really like you needed a helicopter skills, pilot skills to open it. If not done correctly, it would just fly away. To the right here was our bias power supply, which is a 20 kilovolt 5 ampere unit. So we call it was big as a phone booth, so we call it the phone booth. It was very overkill, but that's what we had. So, and we used this one for etching. As far as I know, this paper presents the first results that are from the industrial side. This was first presented at the Society of Vacuum Coaters conference in 2003. I think the SVC has and still is an important forum for the development of HiPIMS. In this work was done at Intervac by De Koven and his colleagues in collaboration with Advanced Energy and Andre Anders at Lawrence Berkeley Laboratory. And at the time, Advanced Energy were working on HiPIMS power supplies, but at least to my knowledge, they don't do that anymore. In this work, they studied carbon. They did see film densification and high ionization in the plasma, but they did not get hard coatings. But they still suggested that HiPIMS will have a bright future. In parallel to the previously presented work, Sheffield Hallam University and a Polish company called Advanced Converters developed industrial HiPIMS, and they implemented this in a Hauser coating machine at Sheffield Hallam University. Advanced Converters, they later become part of the Trumpf group, and these power supplies, they are still available under the Trumpf-Hüttinger brand. This work was presented at the 2004 SVC conference. They report a peak current of more than 2,500 amperes with a stable electronic arc suppression over hours. And they see a highly dense plasma containing also doubly charged titanium ions and very high metal to ion neutral ratios. They also report on that the time evolution of the discharge show a transition from gas to metal plasma within the pulse. And they also concludes that a higher power of gives more ions in the plasma. In 2005, the owners of Chemfield decided to restart the activities after some years of low activity. The name ion sputtering was added to the company to better reflect to its future activities. A small team of scientists and entrepreneurs were hired, and a production agreement was signed with the local electronics company called Angland Electronics. At this time, I was still a student, but I joined the Chemfield ion sputtering in 2006. At the time, the company was developing a series of more flexible and smaller HiPIMS power supply. We called them the CNEX. This top picture here is a picture of a CNEX power supply. All of these were in the area. All of these activities were in the area around Linköping and in close collaboration with Linköping University. And the idea here in the early days was to promote HiPIMS and team up with key actors in PVD. And we wanted to develop processes, hardware, and find applications for HiPIMS. As a part of this, we traveled around the world trying to market this technology. This picture here is from Tokyo Big Site in 2007, and it's Professor Greg Grushinsky and me. These pictures and articles were published in Sweden's biggest newspaper for engineers called Ny Teknik, and it's in Swedish, but it says pulsed sputtering gives stronger cutting tools, and Linköping gets a new surface facility. In 2006, Chemfield Ion Sputtering signed an agreement with the German company Semicon. The agreement was that Chemfield Ion Sputtering would supply HiPIMS power supplies to Semicon, and that the team should do joint R&D together with the Linköping University. As a part of this collaboration, a Semicon coater was equipped with HiPIMS and placed at Linköping University. This machine is still standing at the university, being used for R&D. And the people here are Walter May and Rainer Kremer from Semicon, Johan Karlsson and me from Chemfield Ion Sputtering. In 2008, Semicon took over the technology and the IP from Chemfield Ion Sputtering and continued their development on their own. And in 2010, they launched the first industrial HiPIMS coatings. At least to my knowledge, this was the first industrial coating that you could buy both as job coating and you could buy also the furnace to do it. But Semicon also continued their cooperation with Linköping University after that. And then in 2008, I left the HiPIMS community and I went to work in the cutting tool industry. So from now on, I follow the technology from a user point of view. And around these years, more and more activities within HiPIMS happens, and it gets more difficult to get a good overview of what is going on. I also want to mention some other persons and organizations that were active back in the days. Both Magpuls and Melek, they were offering HiPIMS early on, but I'm afraid I'm not too familiar with their stories, but it would be interesting to hear more about it from them. But from 2006 and onwards, the number of patent applications mentioning HiPIMS start to increase drastically, and you can see the number of patents coming from big companies start to increase. And some examples are listed here, like Hauser, Oerlikon, Semicon, Fraunhofer, Hittinger, Gillette, Sandvik, Sulzer, Metaplus, and also from Japan, Hitachi and Kobe, and from Sheffield Hallam University. Hauser, they started to offer HiPIMS in their machines in 2010. I believe at the time it was with AC Hittinger power supplies. And Oerlikon Balzers, they launched their SPPP coating technology in 2013 in connection to the Balik family of coatings. And nowadays they call this the better HiPIMS. And over time also other companies have started to offer HiPIMS solutions. Back in the day, C-Pulsar and Sond were very active, and also Nano for Energy and Starfire. And then of course we have the iPhone with the HiPIMS coatings, the iPhone from Apple. And in 2021 Apple launched this iPhone 12 Pro available with the HiPIMS coatings. I don't know much about this. I stumbled across this material when I prepared this presentation, but I found it quite interesting. Also in the timeline, I must briefly mention our own company, Inotics. Inotics started in 2010 based on a need for better and more flexible HiPIMS hardware, and the founders were these three persons. And from our perspective, the market for HiPIMS has gradually changed from being mostly in academia, and there has been a journey into more industrial R&D and into industrial applications. And today you can we also offer fully industrial units. I would like to wrap up with a couple of slides about HiPIMS and cutting tools, since I spent many years within the cutting tool industry. And to my knowledge, the area where HiPIMS has most industrial impact is on cutting tools. And I know Semicon has had good success with HiPIMS, and that early combulsors now have a significant part of their job coating business coming from their SPPP technology. But where is it best applied? Reducing the tool wear is often about connecting the right grade properties to the geometry and wear type. And with grade, I mean the substrate and coating. And to the right here, in these pictures, you saw there are some examples of wear types, and these all put different demand on the coating. Just a simple example, if you have a continuous high heat application, aluminum oxide produced with CVD is most often a good choice. But if you have a more toughness demanding operation, for example in milling, often PVD coatings are more suitable. But how can this thinking be applied to HiPIMS? I say that you get some control of ion bombardment and thereby the residual stress and composition due to resputtering. This can be used as a tool, for example, when it's sensitive to have good coating adhesion in the cutting edge. For many cutting applications, the edge is actually in the stagnated zone and it's not subjected to so much wear. But in some cases, this is not true. And the coating adhesion really in the cutting edge matters. Examples of this can be, for example, parting and grooving, high precision tools, and I'm sure there are also many other types of operations where this is important. This is an example of a test we did at Laminate Technologies about 5-6 years ago. We were amazed with the result. This is a test from in a lathe where a bar is cut off to the center, and since this cutting speed goes to 0 when you reach the center, this puts a lot of demand on the cutting edge. And the tool life limiting factor in this kind of application was chipping due to edge line flaking, and it comes from the adhesive wear on the cutting edge when approaching the center. And in this test, we included our own development, both with an arc coating and with a commercially available HiPIMS coating, in this case from Semicon. And in the test, we also included what was considered to be the market leader for this type of application. And as you see, it's amazing results. You normally don't see this kind of improvements, especially not only from a coating. But the HiPIMS coatings was by far the best in this test, and our analysis showed that it was really due to the better wear resistance in the cutting edge. This is my last slide, and HiPIMS has made its way into being industrially applied for cutting tools. I think it's not going to replace the existing technologies like arc evaporation or CVD, but it has already shown that it's a valuable technology for certain applications. Here I try to make a market estimate based on my own contacts and knowledge. I think somewhere now 5 to 10% of the total job coating market for cutting tools is made with HiPIMS. And if I get this mathematics right, this would correspond to around $500 million. So it's in tooling value. So it's really significant. I think the technology will make the same journey in other fields of applications, and it's going to be interesting to follow. Thank you for listening. And for fun, I asked an artificial intelligence generator to make a picture based on the word HiPIMS, and this is what I got. I'm not sure what it is, but maybe you have ideas. Thank you.